All right. So I'm just going to kind of go through Wednesday's stuff and hit the key points and then see if there's any questions from it, because I know it seems backwards to me that if you can pause that it would be more solid, but I don't know. Maybe you needed to ask some clarifications, and obviously if I wasn't sitting right there, that wouldn't work. So let me go over some key points from Wednesday. In my Monday class, we had to go through that for 2 days because I hadn't even seen them since Friday. So we may actually not finish early, but we'll have enough time to do one of these practice problems in detail at the end. So we'll go through some main points, and then we're going to do a little game with enthalpy, like a little... I compared it to Sudoku, and someone got mad at me afterwards because they were like, that was not nearly as fun as Sudoku. But it's like that, like a little problem-solving thing, okay? All right. So the takeaway from state functions, the stuff I actually care, is that you guys get the definition and the time when we're going to use it, okay? So only depends on the final and initial states. That's the definition that we really care about. And we use this for enthalpy. So I'll recap what enthalpy is in a minute, but it's basically the potential energy change in a reaction. Okay, so what we mean, knowing that enthalpy is a state function allows us to do the mathematical game that we're going to do today. It really just means that we don't have to pay attention and we can actually pretend like stuff happens in the middle as long as the initial and final states are the same. So normally we would think of a process as just going from one point to another, and that's all we care about with enthalpy is what does we start at and what do we end at. But we can pretend mathematically that it does a bunch of this as long as it comes back to the final point in the end. So what I kind of mean by this is, like, let's say we want to do A goes to C. We can do A goes to B and then B goes to C. What is that, like commutative property or something? I don't remember the names of all those. Anyway, something like this. And we will get the same answer if we look at the enthalpy of A goes to B and B goes to C, or if we just look at the enthalpy of A goes directly to C. Okay, so that's what knowing that enthalpy is a state function, that's what that allows us to do. Okay, so big topics we covered in Wednesday's class. Calculating heat, calculating work, and then enthalpy, what it is, and how we can treat it with a chemical equation. Now, heat and work, although they are the common ways for energy to be transferred in a chemical reaction, they can be a little bit tricky to solve for a chemical reaction itself. So to get you started, we solve it for very simple systems. So if you want a reminder, you can come back to this slide. So remember, heat and work, Q and W, is how energy gets transferred between a system and surroundings. Usually we think of this as a chemical reaction, RXN, just an abbreviation for reaction. We're going to do it for something even more simple than a reaction, though. Okay, so you can have heat going in or out of the system. We always look at it from the system's perspective. Engineers tend to look at it from surroundings because they want to know what can they do with that heat or that work. We look at it from the system's perspective. So is heat going in and out of the system? Is work going in or out of the system? And that's how we define the signs. So this is a good review as well because this is going to be quite important. all of the ones that have a negative sign, whether that's just energy overall, or if heat comes out to be negative, or work comes out to be negative, that means that the reaction or the system is giving up something. It's giving up energy, right? The energy diagram would look like this. It's going down in energy. Well, if something goes down in energy, that chunk of energy has to go somewhere. So maybe it comes off as heat. Maybe it comes off as work. Maybe we don't know the specifics and it just comes off as a generic amount of energy. So those signs, when they're negative, that's what that's telling you, is that that's going away from the system. And then the positive is obviously the opposite. It requires something to go up in energy. So either heat has to go in, or work has to go in, or maybe we don't know specifically what it is and we just say energy has to go in. So this is lifting the pencil up. I have to put the energy in, right? Once I'm not putting the energy in anymore, it's not going to stay there. So those signs will always be positive. Okay, so conceptually, you can check the sign of your heat or your work by knowing this. As long as you do a change calculation, always as final minus initial, then you should get the right sign, positive or negative, for any of these calculations. Okay, so that's important to remember. Okay, so simple zoom in on a simple system where we do a heat calculation. Not a reaction, we've just got a chunk of hot metal, okay? That was the funniest when we've only lived here for, I guess this is like the third year. We've almost lived here for 3 years. It just doesn't long time now. Or it feels like it hasn't been that long. Hot metal bridge, that was bizarre. You guys know hot metal bridge downtown? Why? Because you feel like it's gonna rust and fall down? Yeah. When I say a piece of hot metal, that's what I think of, hot metal bridge. It just sounds cool. Okay, so you stick a chunk of metal in some warm or room temperature water, right? We know intuitively that that metal's gonna cool down. In that process, what it's doing is giving heat to the water. Okay, we can calculate that with this equation, Q equals mc delta T. Now we can actually calculate, if we know what the metal is, we can calculate that for the metal, or we could calculate it for the water. We could say how much heat is the water absorbing, right? The metal's giving the water the heat off, the water is absorbing that metal. So, like I said before, change needs to be final minus initial. So when you do a temperature change, you always do final minus initial to get the right sign. And then conceptually, you should know that the metal is going to end up being negative. I think when we did this one, it came out to be like 810. So it's negative because it's giving up that heat. And all this negative means is they have to be the opposite sign. Right? The water is going to be positive 810 joules. Same amount of heat transferred, just who's giving it up and who's taking it. Okay, so you'll need to be able to do calculations with this. A note about specific heat. That value, it's a constant. As long as you know the substance, you can look it up pretty easily or be given it. No, you don't have to memorize anything. What you should understand is the lower these numbers are, the more responsive they are to energy being added in. So if you think of like metal, so all of these are metals up here, they have relatively low specific heats. If you touch a piece of metal, it feels cold because it is immediately absorbing heat from your hand. Okay, it's very good at taking heat away from things. It's also very quick to heat up itself and then also cool down really quickly. So as it's, yes, I was like, what was that example I thought of earlier? I've noticed a couple times if I have a bracelet on and I'm like cooking, all of a sudden I'll be like, oh, what the hell? And I'm like, my bracelet is heated up so quickly that it actually like burns my skin. Obviously that doesn't happen with like my shirt. My shirt doesn't heat up and burn me. That's because metal can absorb that heat that's coming off of the pan really easily, and that its temperature goes up really quickly. Like, I don't know what the specific heat capacity of cotton would be, but it's going to be a lot higher. It's a lot harder for it to absorb heat and change its temperature. So water is like the classic example of this. It takes a whole lot of energy being added into the water to get its temperature to change. So being able to conceptually understand what low and high specific heat capacities mean is useful. I think responsiveness to heat is probably like how the temperature responds. It's probably the best summary definition. Okay, other calculations, you need to be able to do work calculations. Again, as long as you do final minus initial, you'll get the right sign for the work here. Think of the thing, whether it's a gas, whether it's a chemical reaction, if it is pushing, because work is a force, so if it is pushing on something, that is similar to heat being given off. The chemical reaction gives off heat, the Q would be negative. The chemical reaction pushes on something, applies a force, the work would be negative. It's energy leaving the system in some form when you have a negative value for those things. So fairly straightforward calculations. This is our equation there. And like I said, we're not going to do these for like chemical reactions that are complicated. We're just going to do pretty straightforward, like here's a volume change, here's a pressure change. The only thing that might be a little bit more detailed is that you might have to change units, or at least pay attention to them so you know when to change them. So if you are at all shaky on conversion factors, this is the time to go review it. I feel like I drilled it into your heads last semester pretty good. If you weren't with me last semester, that's when you might want to go review that. Okay, so that would be like chapter 2 or 3. And then when we do enthalpy stuff, we're also going to start doing some stoichiometry. So that's chapter 4. If you look in Pearson, there's that practice exam that's in there from semester 1, like final exam practice. And any of the chapter 4 stuff is stoichiometry. 2 and 3 would probably be those conversion factors. Okay, so then the last thing we talked about was enthalpy. I'm not going to use this slide. I'm going to use that one. Maybe I'll erase some of this stuff too. This must have been, your class notes must have been the one that I used for the video because they're all lots of detail on there. Okay, so when we get to enthalpy, the reason why we use enthalpy is because it is a state function, so it's easy to handle. It tells us a lot about how the energy in the bonds, when they're either broken or formed, how those differ between reactants and products, and the very specific type of circumstances that enthalpy is applicable to are super common. So heat at constant pressure is what enthalpy, the real definition of it is. Do you have to know that? Know that it's heat or that it's related to heat. But the biggest thing I want you to think of is potential energy change. So for us, it's similar to those reaction diagrams or those energy diagrams that we showed before, where we're focusing in on how does the energy change between reactants and products. The biggest difference is that we're specifically talking about heat coming off or going in, not work at this point. And the difference between those tells us about the potential energy difference between reactants and products. And this is due to bonds that are being broken or formed. So if you go down, negative because energy is being given off. Yes?
So when you said it's just heat, so when you're looking at enthalpy, you're not looking at work.
Yes, that's right. When you're looking at enthalpy, we've eliminated work from that equation. Yep. And this is really what the rest of the chapter will deal with, is enthalpy. Now, I say that there is one, we're going to skip over those slides, and I'm going to decide on Monday whether we do them or not. But there is one calculation with calorimetry that relates heat and enthalpy a little bit more detailed, but it definitely avoids work. So literally just that 1 or 2 slides about work, what it is, a simple calculation. That's the only thing we're going to do with it. Okay, so when the energy is going down, like down in potential energy, another way of saying that is that the products are more stable. They're at a lower potential energy, they're more stable. We call that exothermic. The sign should be negative, and you should know that you're giving off heat as part of that process. So an example that I thought of in my other class was hand warmers. So like if you go skiing, stick these in your boots or whatever, you snap the thing in the middle and shake it up, and you're reacting. Usually it's just like a metal with like a solid acid or something. And it's an exothermic reaction though. It's a reaction where you're emitting heat, and that's why it feels warm. And then instant ice packs that you keep in like a first aid kit. Exact same thing. You break the thing in the center. Now it's usually 2 salts mixing together. That process is endothermic. Not all salts are like this. Some are, some aren't. But that process is endothermic, so it requires heat, and the heat it requires comes from you, right? You stick it on your head, and it pulls the heat out of your head into the ice pack so that the chemical reaction can go up in energy. So the delta H should be positive there, and we call it endothermic. Okay, now recap on how we use enthalpy and like manipulations. Actually skip that one for now and go to these rules. Okay, so if you have a reaction and it shows you the enthalpy, it means for the reaction written as it's written. So in this example, that is for 1 mole of carbon and 1 mole of oxygen, forming 1 mole of CO2. So if I want 2 moles, I gotta multiply that enthalpy by 2. It scales just the same way that moles scales. And then similarly, if I have this reaction where heat is coming off, right? It tells us that, now I can write it as negative just so no one gets confused. By drawing the arrow as saying it's coming off, I'm implying that it's negative, okay? So if I want to go the reverse way, I have to actually combine that 393.5 kilojoules with the CO2 if I want it to go back to carbon and oxygen. Okay, so that means if I write the reaction in the reverse direction, like it is down here, that I need to change the sign. The amount stays the same, I just change the sign of the enthalpy. So we are gonna use these rules now to play that game I was talking about, where we're gonna manipulate equations and figure out enthalpy values for reactions where we don't know the enthalpy values. Okay, so how are we going to do that? These are the 2 slides we're skipping over. We'll come back to them or not. I'm going to decide later. Okay, so this is that thing that I told you about like we can think of a reaction as happening in one single step, or we can think about it in happening in multiple steps. So let's pretend that we don't know this enthalpy. We want to know it, but we don't know what it is. Well, there's kind of 2 options. We could go in a lab and set up the experiment and run it and measure the enthalpy. That would be kind of expensive and time consuming. Another way that we can do, because we know that this works out, is we can look up some reactions where we know their enthalpy values and use the fact that if we can get from the start to the finish, then we can just calculate it based on those previous steps. So here, this is saying A plus 2B makes C, right? So let's write that down. A plus 2B makes C. And then in the second step, C goes to 2D. Okay? Just like if it was a mathematical equation and the arrow was an equal sign, if I have X on both sides, right, I can just cancel it out. Or if I have 5 on both sides, I can just cancel it out. So when I add together equations, what I'm saying is that things that are the same on both sides would add together. Things that are opposites, one on either side, they're going to cancel out. So I'm going to add reactions together, and then I'm going to cancel out anything that's the same, in this case the C. And if I can get it to the point where it matches up with the thing I want it to be, then I can just add these guys' enthalpies as well. If I add their reactions, I can add their enthalpies, and that'll give me this new enthalpy, the one that I don't know. So this process is called Hess's Law, and we're going to do one together, and then I'll give you guys a little bit more complicated one to try with your neighbors or on your own. Okay, similar to what we just looked at, 2-step or 2 reactions that we know their enthalpy values for, and one that we don't. So it's kind of this idea of right here, we know this one, we know that one, this is the one we're looking for. So what we need to do is we are going to manipulate these equations that we know, and by manipulate I mean flip them around or multiply them by a coefficient. Eventually, I'm going to add them together. The goal being to do those things so that this matches up with what that one looks like. So that all the chemical species have the right number of moles and they're on the right side and there's nothing we don't want. And as we do that, we're going to do the exact same thing to the enthalpies too, so that ultimately we can get the reaction to look the same, and then the enthalpy will look the same. And that'll tell us in a calculation way instead of an experiment way how to find the enthalpy of this reaction. Okay, so there's 2 kind of approaches you can take here. Because I'm only going to give you a limited number of known reactions, so these are our known reactions. I'll call this one the unknown. Sometimes I'll say it's the goal reaction, like what you're trying to get those others to look like. So there's only a limited number of them, and you're going to use all of them. It's not like I'm going to give you some, distractor one that you're not going to end up needing. So you could look at these reactions and say, what do I need to do to them to make them match this one? So that's where we'll start. And then in the next problem, maybe we'll look at it in the reverse direction and say, this is what I know I need. How do I use these reactions to match up with what I need? Okay? All right, so let's just look at reaction 1. It's got NH3 in it, N2, and H2. So when I look at my goal reaction, I've got NH3 in that one. I've got N2 in that one. I don't have any H2 though. So, oh well. We can't take parts of a reaction, so we're just going to do something with it, and we'll have to worry about that H2 later. We're going to have to get rid of it somehow, is the short story. Okay, so let's start with the NH3, just because that's the thing at the beginning of reaction 1. So where does it appear in this reaction? Well, it's on the product side in the goal reaction, and in reaction 1, it's on the reactant side. So immediately I know that that's going to be a problem, because if I want these guys to look like that one, then I need to flip that around so that it's on the product side. Okay, so that's the first manipulation that I'm going to do. I'm going to take reaction 1 and I'm going to flip it around. So flip reaction 1. So I'm going to rewrite it in the reverse direction. I'm going to make the products the reactants and the reactants the products. Again, the idea is that I want it to match the goal reaction. The thing that I don't know the enthalpy for, I want it to look like that. So I'm just trying to get the NH3 to look like the NH3 in the reaction above. Whenever I do something to a reaction, though, I need to do it to the enthalpy as well. So I'm going to take that delta H and I'm going to just change the sign, because when I flip a reaction, it's the same amount of heat, it's just now it's released instead of absorbed. Okay, so I've made a very small step at making this NH3 look like that NH3. Next step, I need to have 4 moles of it, right? Instead of just 1. So it's on the correct side, but I need the right number of it. So I'm going to now take this flipped reaction and I'm going to multiply it by 4 so that I get those 4 NH3s, because I'm trying to make it look just like the one above. So I have to do this to everything in the reaction, not just the NH3. So I end up with 2 N2s and 6 H2s, 4 NH3s, and times 4, 184. So I have to do it to the enthalpy as well. Okay, now it looks like I'm starting to get somewhere with that NH3. So I've got 4 NH3s in the goal reaction on the product side, and now I have 4 NH3s in the manipulated known reactions on the product side. Okay, along with that came 2 N2s and 6 H2s. The N2s, oh, how convenient. 2 N2s on the reactant side, 2 N2s on this reactant side. 2 N2s on the reactant side, 2 N2s on this reactant side. 2 N2s on the reactant side, 2 N2s on this reactant side. 2 N2s on this reactant side, 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 2 okay? So I've now got basically half the reaction the way I want it. Yes, I'm gonna have to do something with those H2s, but they're probably gonna work themselves out. But be aware, because in the next example, the one you guys are going to work on your own a bit, you have to get rid of the things you don't want. So you have to get the things you do want and get rid of the things you don't want. All right, so we've used reaction 1. Let's look at how can we use reaction 2 to get ourselves, hopefully, all the way there. Okay, there's hydrogen again. So like maybe we can use that reaction to get rid of the hydrogen. That's a good way of thinking about it. Another way to think about it is I have O2 and I need to get 3 O2s on my product side. Another way to think about it is I've got H2O and I need to get 6 H2Os on my reactant side. So deal with one of the things. Let's start by dealing with trying to get one of the things rather than trying to get rid of, okay? So let's look at the waters, all right? It wants 6 waters on the reactant side. Reaction 2 has 2 waters and it's on the product side. So I'm gonna do this one in 1 step. You can do it in 2 steps if you want, but I'm going to flip the reaction and I'm gonna multiply it by 3. So this is how I like to keep track of what I'm going to be doing. And let me like write it next to it instead of on the side there. I like to write down what I'm gonna do to the reaction, both to the reaction itself and to the delta H to remind myself what I'm doing. So a negative means I'm flipping it because that's what you do to the delta H is you multiply it by -1. How did I manage that today? Okay, and then I'm multiplying it by 3. So I'm going to do this in 1 step. If it makes you feel more comfortable, do it in 2. So flipping it around, I have the water on the reactant side and multiplying it by 3. So I have 6 H2O. Six H2 and 3 O2. Okay, so flip the sign, should be positive now, and times 3 should be 1,452. Oh, geez, I can't lose it completely. I think that doesn't change the brightness for you guys. There we go. Okay, so now I've got my 6H2O that I wanted here on the reactant side. I've got my 3 O2s that I wanted there. And if they're on opposite sides, they cancel out. So the 6 H2s cancel out. So to kind of summarize this even more, if I'm adding them together, I'm going to write all of the reactants together. And I'm going to write all of the products together. And then I'm just going to cancel out anything that's the same on both sides. So now I'm left with exactly what I had above. 2N2 plus 6H2O plus 4NH3 plus 3O2. Doesn't matter that the O2 and the NH3 are flipped. I just happen to write it that way. So I added the reactions. I'm going to add those manipulated H values. And I get that delta H for this reaction is 1,268 kilojoules. Yeah.
Do they have to be the same coefficient to cancel also?
Yes. Yeah. In fact, you'll see in another one, but like if it was 3 and 6, then 3 of them would cancel out, but the other 3 would remain. Yeah. Okay, so this will make a lot more sense once you do a practice example on your own or, you know, with a neighbor, but okay, so on the next one, let me just give you one tip. Do not try to mess around with the hydrogens first. So if you see you need hydrogen, you need 1 mole of it, but there's like 2 different places where hydrogen appears. So don't do that one first. Basically just don't play with the middle reaction till the end. Let's say that, okay? So mess around with the first and the third reaction to try to get to this goal. Okay, we're trying to find out the delta H of this. But leave that middle reaction till the end. And like I said before, you have to get what you want, but then you also have to get rid of what you don't want. So for this one, you're going to end up, your last step is going to be getting rid of what you don't want, even though you have all the things you already want. Okay, so take some time. My last classes took, like, we worked on it for the rest of the class time. So we'll probably do 8, 10 minutes at the most for you guys to try to work through it, and then we'll finish it up together. I probably will give a hint or two, assuming my iPad doesn't die, up on the board, you know, in a few minutes. What I'll do it as is I'll say like, oh, times 2 or times -2 or something to indicate how you're going to manipulate the reaction. But I want you guys to struggle with it a bit to start. Okay? And I'm going to, hopefully everyone has their notes open. I'm going to turn this off for a second in the hopes of saving my battery.